Good morning to one and all. On behalf of Konganadu College of Engineering and Technology, we welcome you all for DPT sponsored one-day national level seminar on future trends of biodegradable packaging in food industries. It's a glad welcome we bring you this morning filled with desires, hopes and dreams we all share. Small share and great welcome makes a merry feast. Now I would like to invite Mr. V. Sriram, HOD, Department of Chemistry, to give welcome address. Welcome, sir.
Thank you, ma'am. Good morning, everybody. All of you present in this DBT sponsored one day national level seminar on future trends of biodegradable packaging in food industry are warmly welcomed on behalf of Kongunadu College of Engineering and Technology, Trichy. I am more than grateful to stand here and welcome you all to this one day seminar. Firstly, I would like to thank the management, Kongunadu College of Engineering and Technology, for granting permission to organize the seminar for the benefit of student community, faculty members, and researchers. It gives me immense pleasure to welcome our beloved chairman, Dr. P.S.K. Periswamy sir, in this occasion. I heartily welcome our respected principal, Dr. R. Ashokan sir, for this one-day seminar. A very warm welcome to the honorable chief guest of this one-day seminar, Dr. S.P. Chidambaram, formerly Senior Scientist, Honeywell Technologies India, and Dr. S. Vijay Kumar, formerly Senior Scientist, SPIC Private Limited, and Dean Projects, KNCET, Trichy. I welcome our Dean, R&D, Dr. J. Egopriya ma'am, in this occasion. Welcome you, ma'am. It gives me pleasure to welcome our first-year HOD, Dr. K. Balasubramaniam sir, and coordinator Mr. N. Kannan sir in this one-day seminar. We welcome you, sir. I also welcome the heads of various departments, faculty members, students, research scholars of KNCET, as well as from various institutions who are participating in this one-day seminar. Definitely, the seminar will illuminate your minds on future trends in biodegradable food packaging industry. I welcome you all once again. Thank you.
Thank you, sir. Now I would like to invite Dr. J. Yogapriya ma'am, Dean R&D, KNCT, to give felicitation address. Welcome, ma'am.
Mm. Thank you, ma'am, and good morning, all and all present here. Am I audible?
Yeah, ma'am.
Okay. Thank you, Mageshwari, ma'am.
Thank you, ma'am.
So, good morning, all and all present here. Today, we have gathered here for the one-day national level seminar on future trends of biodegradable packaging in food industry, which was sponsored by Department of Biotechnology. For that purpose, we have initially started, that is 3 months before, we have submitted this proposal with the help of Dr. Vijay Kumar sir, and this proposal was written by Vijay Kumar sir and Kalimagal madam, which was clearly guided by the Vijay Kumar sir. And recent trends in recent years, the biodegradable packaging is very important for an food industry. With the keep of mind in the biodegradable packaging, the Vijay Kumar sir and Kalimahal madam has written this proposal clearly, and this seminar definitely will address you how the packaging will be done by using biodegradable materials in food industries. And for that purpose, I would like to thank DBT, who has accepted a proposal to conduct this event. And also, in recent years, we are using in plastic and all for whatever we are carrying out for an food like vegetables or whatever we are going to buy it, right? Now the government has stopped to use the plastic. So instead of that, that trend moving towards in government also, they are changing the mindset. Definitely everyone should use in biodegradable plastic. So they are definitely, this seminar will address you what are the materials being used, how the packaging will be done, and it will be useful for carrying the food, as well as it will be useful for the food industry. So this session will be handled initially by Dr. S.P. Chidambaram sir, formerly Senior Scientist, Honeywell Technologies India, and afternoon session will be handled by Dr. S. Vijay Kumar sir, and Dean Project and Consultancy, Kongunadu College of Engineering and Technology. Before that, he has worked in various industries, speak and all, with relevant to the research. And also I thank everyone, I thank all the participants who have joined here to learn the biodegradable packaging and food industry. Definitely the seminar will address you, whatever you want, it will be clearly mentioned by this two professors. And also the evening afternoon session also, it will be a practical session, will be handled by the Vijay Kumar sir. He is also having an industry with relevant to biodegradable packaging. I would like to thank everyone for joining us, and also it should be an interactive session. It will be helpful for you for your further research, and also I inform every participants to learn about this, and also inform your students, guide the students to do more projects relevant to biodegradable packaging and what kind of materials, everything used. It will be definitely the future era will be in biodegradable packaging only. So I thank DBT and our management principal sir and HOD of SNH and chemistry HOD and Kalemagal and all the faculty members of chemistry department who have taken enough step to start this submit the proposal and get the grant. And now today we are in the end of session, that is we are going to organize this program, and lot of interactive sessions also will be there. So I thank everyone for joining this, and also I thank all the two keynote speakers for accepting our invitation irrespective of this busy schedule. Thank you, Ananda.
Thank you, ma'am, for your brief intro about biodegradable packaging in food industry. Now, I would like to invite Ms. P. Suganya, Assistant Professor, Department of Chemistry, Konganadu College of Engineering Technology, to give chief guest introduction. Welcome, ma'am.
Thank you, ma'am. May I audible, ma'am? Maheshwari, ma'am.
Yeah, ma'am. Yes.
Okay. Now I cordially invite our chief guest, Dr. Chidambaram SP. His education qualification, he has completed Master of Science from Madras University and Doctorate of Philosophy from IIT Madras. Then his working experience, he had 25 plus experience in research and technology management and material development, then planning and customer support. He is a versatile and peculiar leader with a good leadership skill. Then he has 30 plus experience in teaching field also. Then he had worked with an analyst in Honeywell Tech Center. Then he is a good researcher, project manager at SABIC Research Technology Vadodara. Then he has involved to work with an analytical research and planting support at GE Plastic Bangalore. Then he is one of the most upcoming industrialists in agrochemical, and he has more ability to produce a new techniques at Speak Tuticon. Then he has published 24 papers, then 4 patents. Then he is working as a director, researcher in Innovation Cell, India's Institute of Technology, Madras. Thank you, sir. Once again, I welcome you, sir. Now this is your time to take over the session, sir. Thank you.
Thank you very much. Am I audible?
Yes, sir.
Yes. Yeah. Okay. First of all, I would like to thank the Kongunadu College of Engineering and Technology Management and team for inviting me, especially Mr. Sriram, HOD of Chemistry, Dr. Yoga Priya, Dean, KNCET, Dr. Rashokan, Principal, and Mr. Dr. Priyasamy, sir. And my special thanks to Dr. Vijay Kumar, who was my colleague.
Thank you.
As well as, and currently the Dean Research, who has invited me into this and asking me to share some of my experience in this. I'm very happy to be here because this is the time where I can talk to some of the students who are possibly researchers in future. So if my talk can initiate something in their mind to move towards research, because basically research is something which is very much needed for a country. If you look into the advanced countries like America, their publications, their research work is multifold compared to India or other countries. So to say, if you have more research, more new inventions, basically you are considered as an advanced country. As everyone like to India to be in advanced level, we would like all the students to get into. Basically, ask a question why before going into anything. That's what it is. Now I would like to go into the presentation. I will ask, the presentation is already shared with Mrs. Kalaimagal. I will ask her to make it into the presentation mode. Start with the presentation so that I can talk about that. Can I have the presentation, please?
Yes, sir. Sure, sir.
Basically, the topic is the biopolymers in food packaging alternative. That is what initially we started with. Next slide, please. Before going into the topic, I would like to give a brief introduction about my work in polymer related field. As in the introduction, when I was introduced, I was told I did my MSc in analytical chemistry from Department of Analytical Chemistry, Madras University, then PhD from IT Madras, which is long time back to say. My first job was with Annamala University, where I was teaching for about 3 years, the masters and MPhil PhD students. Then I moved on to the industrial research areas. My first industrial research was with the SPIC R&D Center, which was attached with the SPIC production unit. So we have a lot of exposure to the plant. So whatever plant problems were coming, we were assisting them. So with that, we were into many areas in that. We were exposed to agrochemicals, uh, new products and everything. But with reference to the polymers, in SPIC we were using some water-soluble polymers, especially for wastewater treatment and cooling water treatment like that. With reference to that, my first experience in water-soluble polymers, which is acrylic acid acrylamide-based polymers, where we synthesized and we developed certain low molecular weight water-soluble polymers, which goes into the water treatment purpose. After that, I moved on to GE Plastics. GE is an American company, and they are into plastics. They are one of the leaders in polycarbonates. Polycarbonates are basically used in the automotive screens and interiors are many with the polycarbonates. So if I take a car, it should come for 10 years at least, right? So in a car, when the polycarbonate is added or made into certain parts are made with that, it needs to be long lasting. So if they add with the different kind of additives. One of the additives is a sand polymer, which is a styrene acrylate polymer, which was having making some colors to the polycarbonate over a time of use when it is exposed to overheat like that. So our process was to find out why the coloration was happening, and we found a reason for it, which was implemented in the plant, and successfully it has changed the way of using the sand polymers. But then we moved on to the SABIC research technology. I moved on to that. SABIC is a Saudi Arabian company. They have an R&D center in Vadodara. So we joined there and then was taking care of the analytical section as well as doing some industry related plant supported work also. With reference to the polymers, SABIC is one of the world's largest producers of polyethylene, polypropylene. They also make PET. PET is polyethylene terephthalate. Polyethylene terephthalate is nothing but the polyesters you would have known about. Polyesters. The polyesters is the one which is used in our shirts, polyester shirts. So they make a filament out of it and make the shirt out of that. But the PET was invented by DuPont. So they were trying to find a suitable polymeric material which can be food grade and which not contaminate whatever the content inside that. So they did a lot of research and a lot of molecules, a lot of polymers, but finally end up with finding the PET, the polyethylene terephthalate itself, is very good for food grade packaging. You see the on the right hand side, you see the PET bottles, very commonly used PET bottles for water, drinking water purpose. So this is a food grade material. But the thing is, the same polyethylene terephthalate which is used in the polyester is used in PET also. Only difference is they converted them into higher molecular weight polyethylene terephthalate by using a special process which they have invented, which has changed the total food packaging or water packaging area itself. So now without the PET, people cannot live in food packaging. The bottom is the structure of polyethylene terephthalate. So this is the terephthalic acid along with ethylene groups in that. The ethylene glycol, they take it and then which makes the polyethylene terephthalate. So special process, they make it into high molecular weight, which makes it to the PET bottles. The things where I worked on is, so when the PET bottles are taken, once it's used and it is going for recycling, they heat it, melt it, and then reform the PET bottle. They try to reform the PET bottles. But what happens is that once you heat it, the polymer loses its properties, and then they become low molecular weight, which is not suitable for making PET bottles. So it's like breaking the bigger polymer chain into two. That becomes smaller molecular weight, which is not having the same strength. So in that area, we were working as a chain extenders. That is a small molecule which will join the two broken pieces of the polymers, make it stronger again. So we were making certain molecules which can work in that way. That is one area. And second area is acetaldehyde scavengers. Even though PET is very good polymer, but if you store water for more than say 6 months or 8 months like that, so they make it, but they make package water and take it somewhere in the stack. It is there for 6 months. It will have small amount, a very small amount, ppm level of acetaldehyde, which is not injurious to health, but it will change the taste of the water, which is not liked by the people. So we worked on certain molecules which can be incorporated into it so that acetaldehyde will not be released, it will be captured like that. So next slide, please. So in the next slide, there is another, next I moved on to Honeywell Tech Center, where Honeywell is one of the world leader in polymers. They make a lot of polymers for different applications. So we have an application lab at Gurugram, the Honeywell Center at Gurugram. They established application labs for different polymers of the Honeywell. The one is the polyethylene wax. Polyethylene, you can make long chains, small chains like that. The polyethylene wax is something that is having a very small molecular weight for road applications. If you go to the roads, if you see that you after a rain, a small rain, you will see a lot of potholes and roads is giving up like that. We like after a rain, the road goes really bad. Why is it so? Because when in the road on the when the water stagnate on the road, whatever the truck and other things which are having a rubber tires, so when they run on it with the water, it forms kind of a suction pump. So it sucks out the stones inside the tar, and then so it gets loosened up and removed. So over and over when the trucks are moving around it, so they give up and then potholes are developed and potholes become bigger and then it becomes bad. So the PE wax, what we have worked on is a small molecular weight polyethylene wax. When you mix it with the tar and then roads are paved, basically the polyethylene is hydrophobic in nature. They will repel the water. So it will bind the stones very well, repel the water so that the potholes will not be formed. So that is one application of this, which Honeywell was making a product out of that. And then we were having a technical support from India for that. The second polymer which I worked on is the polyurethane foam. Polyurethane is used in two types. One is a rigid foam and other is a flexible foam. Rigid foam is something which you can see inside every refrigerator walls. This is a very good non-conducting medium, the puff of what we call polyurethane foam. So here we mix two kind of materials. One is the isocyanate, diisocyanate, and polyol. By mixing those in a different way, different kind of polyols, different materials, we can make it as flexible foam as well as rigid foam. Rigid foam is used as a in the refrigerators and all as a insulator. Flexible foam is something which you are sitting on. The mattresses and others, both are polyurethane foam but made with different raw materials. The third one is Aclor. Aclor is the polychlorotrifluoroethylene. So PTFE you would have heard of. Teflon coated materials, non-sticky, Teflon tapes. These are some applications of PTFE, which is polytetrafluoroethylene. So, but this Teflon is hard. You cannot make it for packaging material. So for packaging, we made a different material. This is a chlorotrifluoroethylene. That is, knock off one fluorine out of that, add a chlorine into that ethylene molecule. So one chlorine, trifluoro, three fluorines, and one ethylene. So this is a basic molecule. Polymerize it. It's a very good packaging material. Good grade. It will not emit anything. So that is very nice for packaging. This is used in high grade the tablet packaging, that is which is shown in the picture is shown on the right side top. So it is used for that purpose. We had an application labs and working on. And the fourth polymer which we were trying is the armor, which is a bulletproof vest, which is used for bulletproof vest. This is the application of polyethylene only, but there are in the polyethylene there are different grades. Low density polyethylene, high density polyethylene. So in this case, this is ultra high density polyethylene, very, very high density polyethylene. So Honeywell has a patented technology to take fibers out of it, and from that fiber, they make this bulletproof vest. They are very light, 15 times lighter than the steel plate, but 15 times stronger than the steel as well as with reference to the bulletproof. So people can wear it casually and then get themselves saved against any bullets or any kind of things. So it is used not only in vest, but different applications of this. So we have an application lab in Honeywell and we were using it. Why I am bringing all this thing is to tell the students that same material with the differentiation, you can get application for different requirements. Polyethylene, low density, high density, different things. So this is the background of the polymers where I was working on, and now I move on to the actual picture of packaging polymers and other things. Can I move to the next slide, please? This is about the polymers, next slide. So in this one, so as I was telling, the polymers, some examples of the polymers, basically the polyolefins, which is low density polyethylene, LDPE, HDPE, the polystyrene, polyvinyl chloride, and polyesters, polycarbonates, many things. So you cannot think of living without polymers. If you look into yourself, currently what you are having, you see that how many polymer things you are carrying it or using it unknowingly. Your water bottle is polymer, your pen is a polymer, your mobile phone has polymers, your vehicles have polymers. So everything has polymers in it. So polymer classification, if you look into that, they are homopolymers. Homopolymers is nothing but you have the same repeating units, like ethylene, polyethylene. It has only the same polymeric unit, same monomeric units with its ethylene. Heteropolymers, like what I was telling, the sand, styrene, acrylonitrile. There are two different monomers into that. Then we can classify them by molecular structure, whether they are linear or branched. by the polymerization process. Addition polymer, which is a polyethylene and all, is a addition polymer. A polyesters like the PET, what I was talking about, they are condensation polymers. Then application wise, there are some thermoplastics. So like the tableting, which I was telling, PCTAP. So heat it. So once you reach a TG, which is a glass transition temperature. So once you have the glass transition temperature, it can be made into different form, like extrusions and different things are possible. But the thermosetting polymer, so heat it, set it. So backlight is an example of thermosetting. So once you made it into certain form, after that you cannot redo that again. Recycling is difficult in those cases. So polymers are very good. Without that you cannot live. But the negative side of it is it doesn't decompose. It doesn't decompose for years. Like this. Next slide, please. So in this one, if you look into that, these are the biodegradability. Biodegradability means what? So you take some material, you put it in normal weathering condition outside, it's degrade into the smaller units or monomeric units like that. So if you look into the different materials which are listed here, cotton, paper, they're normally for say 1 to 6 months, something like that. Leather shoes maybe take 25, 40 years, something like that. But the plastic bags, the small bags which you are carrying, it will go into smaller pieces, but even though it will not go to the monomers, but it will go into smaller pieces, maybe 20 years, 25 years like that. If the plastic becomes thicker, more than that, 400 years, 450 years. But some of the polymers will never get decomposed. So that is a problem. So these are all like fossil fuel based polymers, what we call. So they are very useful, but they don't degrade. So it create problem. It gets accumulated year and year. So whatever millions of tons which is produced every year, getting accumulated. Next slide, please. So these are the monomeric units, generally what we are talking about. The first one is polyethylene, and the squared area is a ethylene monomer. So like that, polypropylene, the left side is a polyvinyl chloride. It has a chlorine in it. Polystyrene, so styrene monomeric unit are shown here. So in addition to that, you see certain triangles in this with the numbers 2, 3, 4, 6, like that. So what are they? So the next slide, please. This is the number of recycles what this polymer can undergo. Like polyethylene terephthalate, what we are talking, the bottles and all. The one is a number which shows it can have a one-time recycle. After that, it is not much used. HDPE 2 times, polyvinyl chloride 3 times, LDPE 4, PP6, PP5, like that. So even though you can recycle it, anything you recycle, because you expose them to certain hot temperatures to get it into the original form and recycle. But the recycling, the properties goes down. Either they become colored, either they become brittle, like that. You would have seen the tubs and other things, plastic mugs and tubs which are used. So virgin polymers, they say, which is the first time they bring it. The recycled polymers is something which they recycle it and bring it. You would have noticed that their strength is less in this case. Next slide, please. Now let us go into the food packaging. Conventionally, so we were using the paper like on the left side. So this is the way we were in India, at least we were doing it, even though some places we get this kind of food packaging. Though it is not good, but this is highly biodegradable. Everything is biodegradable in the left side. But for ease of use, we have started using the plastic bags, carry bags, and then like milk and whatever it is, it comes in that packaging type. So we use it and throw it. So you throw that, your children, your grandchildren will still keep seeing that because the decomposition will take hundreds of years for that. That is a problem of all this. Next slide. When you go to the food packaging, so what is the necessity of packaging the food? Basically, if you look into that, 1/3 of whatever produce we make that get lost or wasted because of the poor packaging, poor maintaining it from the food cycle. If you take it from the harvesting to the eating, so you have it passes through number of hands, and then any place something will happen to that if it is not properly packaged. So it is lost, it's wasted. So whatever reduced food waste, if you can reduce it, it is like increase the food production. So now the population is increasing so much, the requirement of food is also increasing. So it is necessary for us to really preserve food rather than wasting. If you come to the in general function of packaging, so if I take any packaging material, like I was talking one of the packaging material, PCTFE, where I was having these tablets getting packed. The first function is to protect it. So if I carry, say you would have seen, say tomatoes or brinjals, which has been taken in the food I like. So they take it and then they sell it 1 day, 2 day, it goes, some amount will get wasted, but it goes. But can you take uh, eggs in such kind of packaging? If you take the egg in a open vessel, open things like that, maybe 50% or 70% will get lost while transport itself. So there is a separate packaging material which is prepared for that, for the eggs to be transported. So the first function is protect the material which it is being taken or packaged, preserve it so that it will be carried and then taken. And practical. So your packaging type should be like the practical methods to be used in the sense that you cannot put apple or eggs, different things into that. It becomes a separate packaging mechanism for each type of preservations in that, and avoid the contaminant. So it should not say if I put a food material like a pizza box or something like that, so that it'll keep that inside that, preserve it so that it will not get contaminated from outside, uh, whatever the dust and other things like that. And also the packaging should have the communication medium. So whoever is want to sell it, it's a marketing tool, so it will have their printing and everything in that. So like that, it should have all these informations when you're thinking about making a packaging material. Next slide, please. With reference to food packaging, you need more. It's not only the protecting the material, so it should have the food, the packaged food should be safe to eat. So after 6 months, it is in the shelf, and then after that, people are taking and eating it. It should be safe for them to eat. Say, for example, if you put a printing ink, which is not suitable for the particular type of food material which you are packing, and the printing ink will get dissolved and it goes into the food material, then no, you cannot eat it. It's not safe for the people to eat. So the selection should be in such a way that it should not migrate. Like what I was telling, acetaldehyde in PET bottles, it should not migrate. So we need to have some mechanism to prevent it so that it is safe for the people to eat it. And the packaging material should be taste and smell neutral. So it should not produce a separate smell into the food material which is being packed. food is taken for its taste as well as smell. If the smell is lost, say the packaging material is not good and smell goes away, it's not good for the people to really eat it. And certain food packaging materials need barrier to light, oxygen barrier is needed mainly to for the material for the things like eatables like fruits and other things. If you have less amount of oxygen, water vapor barriers, if these things are there, barriers are there, it will have more shelf life in those areas. Barrier to CO2, barrier to aroma, these are some other requirements. So the best example is PET. PET bottles, you can use it for cold or room temperature filling only. If it is more than 60 degrees, it will de-shape because the TG is around 60%. So for that reason only, this food packaging, this is especially if you look into the um, jam bottles. Jam bottles are still jam are filled only in glass containers. Though PET is suitable and it will matches all the things, but jam will be packed at high temperature. They heat it and hot temperature they will pack it. So if you put it more than 60 degrees, the PET is not suitable for it. Machinability and sealing properties, like the bags what you are making, polyethylene bags. If you do it by hand method, like egg containers and all, where which is a paper making, which are handmade, you can make only a small amount of the packaging materials. So it should have a miscibility and sealing property for all packaging. The other is the reuse and recycling, like the number 1, 2, 3, 4, which I shown few slides before. So you need, if you have more number of recycling possibilities, that is good. The price should be obviously cheaper. Next, oxidation or rancid properties. Rancid means what? If you keep oil for more than 6 months, 10 months, it becomes rancid. It will have a smell, it will have taste difference like that. So if the food packaging material, what you are selecting, if it is preventing this kind of an oxidation, that is good. And for other food materials like bacterial growth and mold growth, they add some additives to that to reduce it, so that the bacterial attack will be minimized. So these are the requirements of the food packaging. Now go to the next slide. If you look into all these requirements, the best materials are the synthetic polymers. They are good, they are very minimum, like PET bottles. They are very good food grade materials. The polyamides, polyolefins, all these things are used for long years. Worldwide production in 2010 data is 270 million tons of plastics, of which the packaging industry itself consumes 110. Almost like 40% is used in packaging. The food packaging, your tablets and whatever it is. So the packaging industry together to say 110 million. The fossil-based polymers, they are very stable, but non-biodegradable. So it 110 millions get accumulated. So every year 100 million tons of plastics get accumulated. Then the world become the plastic waste dump yard. Like so, every country is focusing now to avoid the single-use plastics like carry bags, and because you cannot avoid plastics, because everywhere we are using plastic. Your computer has plastic parts, so everything is plastic, so you cannot avoid, but to the extent possible can be reduced with single-use plastic, which is a carry bags and other things at all. So next slide, please. So some of the very small attempt in India and other places are the, the, the cutleries and small items which you can replace with the biodegradable materials. The 2018 there is a data that biodegradable cutleries, that is from natural sources, they make it so which is around 33.9 millions. There are some companies which are listed here. They make cutleries out of the rice banana stem like that. These are the companies which are listed. But in India, we are already using it. The Tonnai and Pakumara plate, etc., and all. These are all biodegradable only. There are certain companies which are listed here. NRDC is offering the biodegradable cutlery technology also. They make some additives with it so that it becomes more stable, more fashionable, so that marketable materials. Next slide, please. Others, hello. So the next slide shows the edible cutlery. This is a new concept of eat your cutlery. So these cutleries are made with material which are eatable, food components, so that they like godumama or something like that. So that you make the cutlery with some additives, they become hard. You make it as a spoon. So you drink your soup with a spoon as well as eat a spoon also. Wheat bran and different materials. The next slide, there is a video, probably you can see that in the YouTube using this word, but I'll move on to the next slide, which is edible biofilms. Biofilms is something where the small eatable materials, instead of packaging in plastics, so you can package it in the eatable biofilm itself. It's like sodium alginate or some other things they make it, the proteins based ones, polysaccharide based ones. So that this package comes, the food material comes in the package. You need not open the package, you eat with that. But these are all very, very small applications with reference to the biomaterials. The next slide. This is another important aspect of preserving the material while transport. That is, so normally when we take any fruit or any vegetable, once you from harvesting to the end user, it will take minimum of 4 days to 5 days. You see, the kiwi is coming from abroad, it may take even more than that. So the fruits and other things should maintain its nature without having any other problems with that. So what people were talking about is the edible coatings. The coatings, like the best material is chitosan, which is a natural product, natural polymer, say. So you take it and then apply it over the vegetable or fruits material. So that it will avoid, it will reduce the permeability of oxygen. So once the oxygen permeability to the fruit is reduced, the ripening process will delay. So maybe the right side top. Hello. So the right side top, you see the fruit, which is 10 days old without using coating, and the coated one, which is seen after 16 days, 21 days. To say it helps in increasing the shelf life of the products. So this is one of the applications for the natural bio-based polymers edible coatings. Next slide, please. Now we'll go to the biodegradable polymers. By definition, what is biodegradable is material that are broken down by natural process into non-toxic reusable substances. So after some time, the biodegradable polymers, if you take it, if you put it in the normal atmosphere outside, after some time they become like into smaller pieces, so that it will not have its original picture or something. Next slide, please. The bioplastics is the general word used in biodegradable polymers area. So the Plastics, the biodegradable, biosourced plastics, to say, there are two types. One is normal plastics like polyethylene can be made from the biosource. Means, say, you have the ethanol, bioethanol, which comes out of the sugar cane. Fermentation, you get bioethanol, CH2, CH2OH. So you dehydrate it, you get ethylene. So you remove one water molecule from ethanol, you get ethylene. Using that ethylene, if you make a polyethylene, they have the same property of polyethylene, but basically it is sourced from the biosource, bioethanol. So this is bio-based plastics. There is a plastic made out of at least or partly from biological methods. Like that, you can make polyethylene, polyethylene terephthalate, PTT, etc. Polypropylene also you can make it. Like basically, it comes from the biosource, but they are not. They are say having the same property of the original polymer itself. The second side is biodegradable plastics, which are basically from the microorganisms, and they get decomposed after some time in the reasonable time frame. When there is a given specific condition, it becomes completely biodegradable, like PLA, PHA, like that, polylactic acid, polybutylene, like that. To say not all bio-based plastics are biodegradable. Like polyethylene is not polyethylene made from biosource is not biodegradable, and not all biodegradable plastics are bio-based. So some of the petrochemical polymers also can be biodegradable, but so it's not necessarily it should be bio-based. These are all generally classified under bioplastics. Next slide, please. Biodegradable plastic, the first one was invented or put into use in 1908. It was produced by Bradenberger. So he has made this cellulose, polysaccharide, basically, cellulose into cellophane. So by making a process to make it into cellophane papers, which we are still using it, they are biodegradable, but the application is limited simply because it's biodegradable. Next slide, please. In this one, it gives the detailed view of what is the biodegradable and non-biodegradable materials, which are from renewable sources or the petrochemical sources. The biodegradable material, that is our important area, is the right side top corner, which is the polylactides, polybutyl butyrate, etc., as well as the material which are coming from the natural sources like wheat gluten, soy protein, like that, and thermoplastic starch, which I will be talking about in the subsequent slides. These are all biodegradable, obtained from renewable sources. There are from petrochemical sources, biodegradable materials are there, which is polycaprolactam and polyglycolic acid and all, which is coming from petrochemical sources but biodegradable. On the left side, if you look into that, the left side top, if you look into that, bio-based polyethylene, like I was explaining earlier, the ethylene comes from the bioethanol, but this is non-biodegradable. Polypropylene, etc., etc. The top, the left side, the bottom is the general plastic which we have discussed here. Next slide, please. So when you come into the biopolymers, there are three types basically. One is purely natural polymers like starch, cellulose, chitosan, etc., which is directly, the polymer itself is taken directly from the biomass. Second type is the polymers, synthetic polymers, which are synthesized from renewable sources like lactic acid. Lactic acid is from the natural source, They take it and convert into synthetic polymer, synthesize it, used into polylactic acid. This is the raw material. The monomer comes from the natural source and the polymer is synthesized. Third one is the microbial polymers. They are polymers from microorganisms like xanthan, gum, and everything. These biopolymers are generally hydrophilic in nature. Hydrophilic means they have attraction towards water. So, in main problem is this polymers when we expose into water vapor or water environment, they are not much used. So these polymers need to be modified by some method to make it more useful for packaging. As I was telling earlier, the packaging has certain requirements. It should be stable first, any environment, for transportation purpose, etc. So if it becomes bad while transportation, it's not useful for commercial purpose. So it needs to be coated or blended with some other material. Modifiers are needed to put into that. Next slide, please. Here I have listed some of the polymers, natural polymers, which decompose or which biodegrade. See, the biodegradability, if you look into that, it should be reasonable time. So 60 days, 120 days, something like that. Within that, it should decompose, it will decompose or degrade into smaller pieces so that we can call them as biodegradable. This is the list. I'm not going into that in detail, but it has all the details of what conditions, how many days it took for them to degrade. Next slide, please. This is a picture of the polylactic acid. So after 80 days, it almost vanishes. The bottle which made of polylactic acid, which degrades in not normal natural environment into pieces and then almost like disintegrate into smaller particles, say in 80 days, which is, so it is classified under biodegradable. Next slide, please. This is a PLA synthesis. I have only one slide in it, and probably Dr. Vijay Kumar in the afternoon or subsequent lecture, he will be covering more into the PLA side of it. Polylactic acid is the molecule which is shown in the left. So if you take polylactic acid and do a condensation reactions, it's alcohol and acid groups are there, so it condenses. It forms a low molecular weight polymer, say with a molecular weight of 2000 to 10,000. But which is not much useful for packaging purpose or any purpose. You need a longer molecule, larger molecule. So they do a chain coupling reaction or like what I was telling SSP in earlier poly PET production side, you do further dehydrative condensation to form a higher molecule. The other method is you make a lactide, which is shown in the right side bottom, the lactide from lactic acid, and then ring opening, you do that and you get a higher molecule. These high molecular weight PLAs are useful for packaging purpose, which will be dealt with Dr. J. Next slide, please. Then I'll touch upon some of the applications of the food packaging and other applications of these biopolymers. Some glimpse only, not going into that in depth. But the thing is, like the first slide, there are certain companies like Cadbury, Walmart, etc., etc. They use these materials like cornstarch trays. They make it PLA cups. They make it PLA trays. They make it jars. They make it, and then they use it for food packaging applications. These are all already commercialized examples for you to see that the food packaging materials, so we can use the biopolymers. Next slide, please. Now I'll go few slides into specific materials, PLA as a packaging material. PLA, it is, as I was telling in the earlier slide, what are the requirements of the packaging? So it gives almost many of them, but some of them are missing. So accordingly, it can be used in packaging certain materials. PLA has high rigidity, good transparency, heat sealability, printability, and processability. So it has a temperature TG at 55. So you can heat it, and then so thermoplastics. So you can heat it, extrude it, it can make it into thin films, it can make it into bags, and etc. So those things are fine. Make it, it's a thermoforming material, so you can do that. And it is classified under generally recognized as safe, GRAS, under FD, US FD. Means that it can be used for food packaging applications. The negative side of it is it has a low glass transition temperature. That means that you cannot carry a cup of tea in this PLA cups. If you take above 55 degrees anything, it becomes somewhat malleable. It loses its shape. It becomes bad. So cold temperature packing, it's fine. Films, it is fine. But there are research going on by varying the LEVO, DEVO isomers and then making the ratios in a different way so that it becomes more rigid, more the TG can be increased by adding some additives, etc. That is going on. So it has, PLA is one of the biopolymers which is used extensively in packaging, food packaging. The next slide, please. Polyhydroxyalkanate is the another biopolymer which is used extensively in food packaging, food compatible material. So especially the poly 3-hydroxybutyrate, which is widely used polymer in packaging. This is again, it's a thermoplastic. It can be extruded, injection molded, thermoformed, etc., etc. The other polymers, the substituted polymers also are in place being used in this. In this case also, there are two setbacks. One is they have a low TG, that is the glass sensation temperature. So high temperature you cannot. Second one is it has a low impact step. So it's not like PET. You throw it from any place, it still remains as a bottle. It breaks. This PHA materials breaks easily. Next one. This is a thermoplastic starch. Starch you may be knowing, the paper bags and everything, these things are there already. So basically the starch is made up of two polysaccharide types, amylose and amylopectin. The same glycoside but has a different linkages. One is linear and other is branched. So it has a mix of the two depending on the source. So depending on that, it becomes either strong or weak. Basically, if you put it in simple terms. So this is very good oxygen barrier, but it is a poor moisture barrier. So if you put a paper bag in water, it gets wet, right? So mechanical property is clear off very easily. So these are some negative side of it, but the things can be modified. Basically, we add plasticizers. Plasticizers means which changes the properties. In polyethylene, like other things also, we use plasticizers. In these cases, if you use certain amount of plasticizers which are cross-linked, which are grafting type like that, vinyl monomers, etc., it changes the properties. So that becomes thermoplastics. Thermal, it can be thermoformed kind of material. It's a glycerol, sorbitol. These are some materials which are popularly used in making the thermoplastic starch. So this is another good bioplastics which are biodecomposable, but still has a number of applications. Next slide, please. Proteins. So you would have heard about the gelatin tablets and other things. This we are commonly using it. These are all basically gelatin is the natural polymer from natural sources. Wheat gluten, soy protein, all these things are used. So like I was telling, eatable films. These are all made with this kind of proteins. They have a good oxygen CO2 barrier, but again, poor moisture barrier. Many of the biomaterials, if you look into that, the basic material, basic unmodified material, they are having poor moisture barriers and low mechanical strength. So again, there are research going on, or modifications are being done to improve the properties, so it becomes more and more. Next slide, please. Chitin chitosan is another important class of material because chitosan has one specific property which is different from other biopolymers. This is actually non-toxic, as well as it is having antimicrobial. That means that if you apply this over a fruit like that, the microbes attack on the fruit also will be reduced. So it's not, if you can apply a wax, simple bee wax or anything like that, which will have a barrier for oxygen, moisture, etc. But chitosan, once you apply it, it becomes antimicrobial. So this is much different from what is used by the other coating. This is very much popularly used in multiple applications. Like the right side has given the applications like healing and food additives, etc., food packaging, etc., etc. Yes. The drawbacks in this case is it has low mechanical, because basically this is a kind of a protein material. It's a low mechanical and thermal stability in these cases. So it needs to be improved by additives. Next slide, please. And I touch upon another area where the biopolymers are used in a big way, is medical applications. Biopolymers are biocompatible, right? So we are biosystems, human beings. So biopolymers are biocompatible. That means that it is compatible with us also. So it will very rarely it get rejected when you put these biopolymers inside our body. If I put a metal screw or nut for fixing a bone, there is a remote possibility you may have some complications because some of the materials may be incompatible with your body and it may get rejected. But think of making a screw or a nut for fixing a bone inside the body using a biopolymer. So it's very rare chances that it gets rejected. So it's a highly biocompatible material. So people started looking at as in medical applications, capsules and tablet coating, which we all know for long period, gelatin tablets and all. Drug delivery. If you take these biopolymers, put some drugs inside that, keep it inside the body for a slow release purpose. So it releases the drug for some time. Once the drug application is used, it dissolves and then just goes into the body and then it disappears. In regenerative medicines, so any transplantation, artificial heart, your breast implant, vascular grafts, etc., etc. It is a big list in that. So in many applications, these biopolymers are finding place. Shuffles and screws, as I was telling, if you make a screw and then fix it, the bits of bone inside the body, so the cells accept that as a part of the body and start proliferation around it, so that it gets into that, it will not have any problem in future. It just get along with the body. And healing the wounds. If you have a very in-depth wound or any fire kind of a accidental skin burnout and everything and all, this kind of chitosan gelatin-based medicines are applied. So basically, they are having its own antimicrobial activities, as well as it will form a thin layer over it, which is biocompatible, and it have a moist environment around it, so that the wounds get healed faster compared to the other medicines. So they have multiple applications as far as the medical applications are concerned. I listed some of them in this for your just information. So next slide, please. So in conclusion, biopolymers currently, if you look into that, it is less than 1% of the total polymers produced. So one is the source is not available. Second one is you need research to make it into more rigid, more compatible, more useful material. So the lot of research scope is there in this area. So in this, of this 1% also, 65% of the total biopolymers produced is used in food packaging only. So the other materials, other applications areas for biopolymers are wide open. So wherever polymers is used, biopolymers can be used as long as it replaces, it has the same property of the fossil-based polymers. So you make it into such a level, and then you have the applications wide open. Currently, biopolymers have less structural stability and moisture resistance. So this is an area where one can work on. So you can have different methods like cross-linking. You add some additives into that, composites. You make it with the different polymers together, and then co-extrusions, multi-layer films, etc. etc. So it needs improvement. Yes, definitely it is there. It is biopolymers needs improvement. So once it is there, it can replace the fossil-based polymers. So more research work is needed, and I would like the young minds who are hearing or participating in this seminar can go into this subject more in depth, and then try to find a place to work on and improve the biopolymers to help the nature, help the human beings, human race. Reduce the fossil fuel based polymers and increase the biopolymers should be the motto of this. Now, next slide. I thank everyone for patient hearing. I hope I have put something into your mind about the biopolymers. And if you have any questions, feel free to ask.
Thank you, Dr. Chidambaram, for your nice presentation. Hello, is it audible?
Yes,
Yeah,
sir.
yeah, thank you.
Yes, sir.
So you are just in brief, at the same time, in detail presentation about the complete scenario of the plastics, right from fossil based to bio based, and without touching much of the chemistry and mechanism or insight to it, but very beautifully presented. And definitely it is going to be an eye-opening for our students, those who have listened to this presentation. And thank you for your valuable sparing your valuable time on behalf of me and on behalf of Comrade College of Engineering Technology. Thank you, Dr. Sundar.
Thank you, Doctor. If you have any questions, if anyone has any questions, and if I know
Yeah.
the answer, I can ask.
So I have a doubt.
Yeah, tell me.
Chidambaram, sir.
Yeah, tell me.
So this is Sudhanya from my Kane set. Sir, I ate a cutlery for the last month. It should minimize my hunger. Is this okay for people's biological system? Sometimes it has produced some unwanted gas. I think it is not okay for me. So how can I eat?
I am not getting your question. Can you repeat it?
So what are the main purpose to initiate this cutlery in this current scenario? Is this
It's a
okay
kind
for
of,
our people?
yeah, right. Your question is right. But the thing is, this is the new way of making the cutlery. So if you wish to eat the cutleries, you can eat it. Otherwise, you can, if you even throw that, this material is made up of biocompatible material. So within a week or 10 days, it will decompose and then it go with the nature. So basically, they are biocompatible or biodecomposable materials. If someone wants to eat it, because you cannot get a feeling of eating a chapati when you are using a cutlery, but this is eatable. This is a new concept, new way of looking at it. If you want, if you like the taste, you can eat it. They have the company who are making it. They say that they make it with the different flavors also, like chocolates and other things and all. So some people like what you are eating, ice cream cones. It's like that only. Ice cream cone, ice cream is ate with the cone. Like that, the cutleries are made. So if you want, if you like, eat it, or at least they are decomposed.
Yes, sir. Thank you.
Any other question?
Sir, one more question, sir. This is Kalamal from Chemistry Department, sir.
சொல்லுங்க.
Sir, these biodegradable plastic now used by most of the people, sir. Is it aware to all the people, sir, all kind of people? This is good for health, and this is good for environment also.
Yeah, this is basically, this is good for the environment. They are currently, the biomaterials are a little more expensive than the fossil-based polymers. So that is one of the reason for less popularity of these bio-based materials. If you make in a comparison, if you take a carry bag of bio-based material or bio-decomposable carry bag compared to a normal carry bag made with a fossil fuel polymer, the bio-based material is more expensive. Basically, material is not available. The processability is difficult, so it becomes slightly more costlier. So my expectation is that over a period, they become equal or compatible kind of things. And this is more of a government focus to convert from the normal fossil-based material to bio-based, so that it will have less impact on the environment.
Sir, one more question, sir. Whether it reaches the low-level people, sir, about the biodegradability and this?
I am not getting you, madam. Can you repeat?
Sir, one more question, sir. Whether this concept reaches the low-level people, sir, about the biodegradability?
I am not sure. சொல்லுங்க விஜயகுமார்.
Madam, it has reached to the core, madam, actually, because since as you know, I'm owning this company, and the product to whom we are selling are very, very average and as well as middle class people. They have the awareness. They specifically asking me a question whether this carry bag is compostable, degradable like that, or it is just putting the logo in a polyester or polyethylene cover. Much awareness are there even in mutton and chicken stall. I have seen it. So this keep on. Moreover, at present in Indian scenario, the only 4% of the total market is being occupied by this bio. And in future, hopefully in by another 4 to 5 years, definitely the market share of this biodegradable plastic is going to touch the maximum level. That's sure. So awareness is there already. No doubt about it.
Yes. Sir, is there any initiatives done by you for creating awareness, sir?
Yeah, there are a lot, not only me, because all that e-Seva Mayam of Tamil Nadu government and the government of India, and wherever the public are assembling, for example, ration shop and other grocery shops, almost they are saying bio bags are available here and boards are there. And now people are there very much fair. Just by feeling the bag, they can able to say whether it is a LDB bag or a bio bag from its softness itself. There's no need to for them to go for any FTR analysis or solvent dissolution, etc. Just by the feeling, they themselves they can able to say. Even in sweet stall, they are giving only the bio bags. Even Adayar Anadabar, very frequently, most of us used to go on the weekends. They are giving only the bio bag. They're getting it from me too. So, moreover, it is costing, as you rightly pointed, compared to the fossil fuel bags, it's 3 to 4 fold rise. But apart from that, considering nature and as well as saving our future generation, this only a peanut. Moreover, it is agri-based and production is low all over the globe. For example, PLA and PBAT are less, and more and more companies are coming up in very soon. So automatically, the supply-demand ratio will be fulfilled.
Okay, sir. Thank you, sir. Dear participant, is there any questions? Please ask now.
In case of no questions, I thank the Kongunadu management and the team for inviting me into this, and I'm thankful to one and all. My wishes to the students who are the future researchers. Thank you very much.
Thank you, Dr. Chidambaram.
Thank you, sir.
So dear participants, please fill the feedback link for the session 1, and the session will resume at 2 o'clock sharply. So please join at 1:50 itself and join the program. Thank you. Suganya ma'am.
Yes, ma'am.
Dear participants, have you get the feedback link?
Ma'am, may I audible?
Yes, ma'am.
Okay. Dear students, will try to put feedback in this link. Once again, I'll try to share our group. The next session will be informed through WhatsApp message. So try to join soon. Thank you.